Welcome back. In this section, we're going to look at two very important theorems, the fundamental theorem of calculus number 1 and fundamental theorem of calculus number 2. The first fundamental theorem of calculus makes a connection between the improper integral and the definite integral. So for this theorem, we start off assuming we've got a function that's continuous. In other words, this function is integrable. And we have some antiderivative, and it doesn't matter which one we have, any antiderivative of our function f. Then if you're looking at the definite integral of f of x from a to b, then that is just our antiderivative evaluated at that upper limit of integration minus the antiderivative evaluated at the lower limit of integration. And any any antiderivative works here, which is the reason why we don't really need to use the constant of integration, because suppose you had some sort of constant of integration included in it. Well, when you evaluate it at b, and then subtract evaluating it at a, the constant of integration would get subtracted from itself and would get canceled out. So when we look at this, when I do the fundamental theorem of calculus, I will find my antiderivative. I'll just leave off that constant of integration, and then I'll evaluate it at the upper limit minus evaluate it at the lower limit. Okay, so let's do a couple of examples. We have this function, x squared minus 3x plus 1, and we're integrating it between 2 and 4. And it is a continuous function. It's continuous over that interval, which means the fundamental theorem of calculus says that all we need to do is find the antiderivative of it. Any antiderivative will do. So I'll use my power rules for integration to do that. And then I just need to evaluate it between 2 and 4. So there's a couple of different notations that people will use. So the one that I'll use here will be put a little bracket, square bracket, and on the bottom, right, that I'm going between 2 and 4. Sometimes people will put a little square bracket on the left. Sometimes instead of a bracket, people will just draw a little vertical line. And they don't always write the x equals, so a lot of times people will just instead write 4 and 2, so indicating that we're evaluating this function between 2 and 4. I'm putting in the 2 and 4 as x equals 2 and x equals 4 for kind of a good reason. We're going to, not too long from now, start looking at cases where maybe we'll do a little substitution of our variables, and so it's always good to sort of keep in mind what variable we're working with. So for myself, when I do this, I'm going to have it written as x equals 2 to x equals 4. And we always evaluate at the top limit of integration. So 4, putting in 4 for everybody. And then minus evaluating it at that lower limit of integration, putting in 2 for everybody. And when I evaluated this earlier, I got that this was 4/3 minus negative 4/3, which gave me 8/3. Okay, let's do another one. We've got a trig function. I've got cosecant, cotangent, and I'm integrating that between pi over 6 and pi over 3. So I know the antiderivative or an antiderivative of cosecant cotangent is negative cosecant. And I'm going to evaluate that between pi over 6 and pi over 3. So we evaluated that top limit of integration, so minus cosecant of pi over 3. And then we subtract evaluating it at the lower limit of integration, minus cosecant of pi over 6. And then just a little bit of evaluating and we're finished. One thing I can do, of course, is since I'm subtracting negative cosecant of pi over 6, that's the same thing as adding positive cosecant of pi over 6, then I just have a little bit of evaluating to do. I know sine of pi over 3 is root 3 over 2, so cosecant should be 2 over root 3. Sine of pi over 6 is a half, so cosecant of pi over 6 should be 2 over 1. So I've got 2 minus 2 over root 3, or if I rationalize that denominator, 2 minus 2 root 3 over 3. Okay, so now here we're getting into a trickier one, and the reason this is trickier is because we've got a function with absolute values in it. So actually, I'm going to do a little bit of work here on the side, and I'm just going to talk about the what's inside our absolute value for a little moment, and then we'll circle back to the integral itself. So if you're just thinking about x squared minus 1, we know what that looks like. That's a parabola that's opening upwards, has a vertex at minus 1, and crosses the x-axis at 1 and at minus 1. So if you're thinking about this, I know that x squared minus 1 is going to be above the x-axis, at the x-axis or above it, when we're below negative 1, and also when we're at 1 and above. And where is it negative? Well, x squared minus 1, that's negative just on that interval from between negative 1 and 1. So what that means for us is if we're thinking about rewriting this absolute value of x squared minus 1 function, we could rewrite it as a piecewise defined function, because for the absolute value function, it does nothing when the function's inside is already positive. So when we're below negative 1, it's just going to keep things as it is, x squared minus 1. It'll do that if we are to the left of negative 1. Also, when we're at 1 and to the right, it's also not going to do anything because, again, x squared minus 1 is already positive. And it's just in the middle, when we're between negative 1 and 1, that the absolute value function is going to do something, and what it's going to do is change the sign, change things from negative to positive. So instead of my function being x squared minus 1, it'll be negative x squared plus 1. It'll change the signs when we're between negative 1 and 1. Okay, so since this function, this x squared minus 1 absolute, really is a piecewise defined function, then for my definite integral, I really need to integrate it in two pieces. It's doing two different things between 0 and 3. Between 0 and 1, it is the function negative x squared plus 1. And then from 1 to 3, it is doing the function x squared minus 1. So now I've got two definite integrals for me to evaluate. I've got the first one going from 0 to 1 and the second one going from 1 to 3. So I'm going to do two little bits of work here. I'm going to first start off with finding the antiderivatives. So for negative x squared plus 1, that's negative x cubed over 3 plus x. And I'm going to evaluate that between 0 and 1. And then we're going to do the same thing for the second integral. We're going to find its antiderivative. For x squared minus x, that'll be x cubed over 3 minus x. And I'm going to evaluate that one between x being 1 and x being 3. So I have two little bits of evaluation to do. So for the first one, evaluating it at 1 and at 0, if I evaluate it at 1, I'll have negative 1/3 plus 1. And when I evaluate it at 0, I'll have 0 cubed plus 0, which is just 0. All right, for the second one, we're evaluating at 3. We'll have 3 cubed over 3, which turns out to be 9. 9 minus 3. And when we evaluate it at 1, we'll have 1/3 minus 1. And then now I just need to finish the little computations that I've got here. So I've got 2/3 minus 0 is 2/3. And then I've got 6 minus negative 2/3, which is 6 plus 2/3. And then I'll add that up, 2/3 and 6 and 2/3, that all adds up to 22/3. So there we go, we found our definite integral of that absolute value function. Okay, one more little problem to look at where it's an area problem. It's the curve bounded by y equals square root of x plus 1, the x-axis, and our lines x equals 1 and x equals 9. So just first off, if I did a little bit of a sketch, this is the square rooting function shifted upwards by 1. So it starts at 0, 1, and then sort of curves off to the right. That's our y equals root of x plus 1. And it's definitely above the x-axis. We're looking for the area bounded by that curve, the line x equals 1, and the line x equals 9. In other words, we want that shaded area. And we said in a previous section that if you're looking at a function that's above the x-axis and you want the area below it, that you can express that in terms of a definite integral. So that's exactly what we've got here. Our area should be the definite integral of square root of x plus 1 from 1 to 9. And now I know how to find this. I don't need to do any Riemann sums or any sort of business there. I can go ahead and use my fundamental theorem of calculus, which says first find any antiderivative. So for x to the half, it's x to the 1/2 plus 1, which is 3/2. Divide by 3/2 plus x. And then we'll evaluate that between x equals 1 and x equals 9. Just to clean that up, that x to the 3/2 divided by 3/2 is the same thing as, if I were to rewrite that, 2x to the 3/2 over 3. So if I were to now evaluate this at 9, I would have 2 times 9 to the 3/2 over 3 plus 9, and then evaluating it at 1, 2 times 1 to the 3/2 over 3 plus 1. So when I clean things up, 9 to the power of 3/2 is 27, so I'd have 2 times 27 over 3 plus 9. So this winds up giving me 18 plus 9, that's 27. And then I'll have 2/3 plus 1, which is 5/3. And 27 minus 5/3, that's 76/3. That's the area under my curve between x equals 1 and x equals 9.